bottom left, you should be able to share your screen.
Yeah.
It's working.
Let me restart. Okay, so today I'm going to be discussing geometric hex meshing. So the idea is you have these quad meshes, and you would like to fill them with geometric hexahedra without refining the boundary any further. So what do I mean by geometric hexahedra? There are different types of hexahedra that are used in different contexts. Usually what we mean is trilinear hexahedra, where you get the space that's filled by a hexahedron is defined by interpolating between the different vertices of the mesh. In some cases, we also consider topological meshes, which is basically if you ignore the geometric problems and you just look at the connectivity, you get a topological mesh. Usually you don't look at, you're not interested in what the topological mesh looks like, but if your topological mesh is correct, it's possible to represent it geometrically with arbitrarily complex curved faces, like here. So it doesn't even have to look like a hexahedron as long as the connectivity is correct. Today I'm going to be discussing geometric hexahedra, where the faces are strictly planar, not almost planar, but each face is exactly a plane. So in this case, the hexahedron is actually a polyhedron. The reason we do this is that it's a mathematically simpler problem, and yet it's still not solved even for very simple cases. What we have known to be solved for a very long time is the topological question. So if you ignore all geometrical concerns, we know exactly when there is a topological mesh, and we can even build one constructively. All of the problems that relate to the existence of a topological mesh come down to the fact that a hexahedron has an even number of faces and a quad has an even number of edges. So you can't have odd numbers of things, otherwise you can't get those, you can't fill those constraints using hex and quads. So the proof was provided by Ericsson, who showed that you could figure, you could find, if you had a hex mesh for these two configurations, which we do, then you can construct for any mesh, for any topological quad mesh that has a topological hex mesh, you can build one just using those two templates. Now, geometrically, if you look at these three examples that have been known for a very long time, we've had for decades topological meshes. Even for the last one, it's obvious that you can have a topological mesh with only two hex, but we haven't had a geometric mesh for any of them. And so that's the question that I'll be looking at today. So this last one, the bicuboid, is kind of one of the more interesting one, because topologically it's the easiest configuration you could have. You only have two hex, but geometrically, if the central four faces don't form a plane, it's not clear that whether or not there is a geometric mesh of this boundary. What's also very interesting about the bicuboid is that if all possible bicuboids have a geometric mesh, then all topological meshes can be extended to a geometric mesh just by refining them a little bit. So the trick to refining them is, first, we don't want the boundary to change. So here, if you look on one side, you have, this is what you would have on the boundary of your mesh. And you can refine it further into a grid of 3x3 quads just by inserting 4 hex. You can do this geometrically, without And so if you apply this template to every face of your mesh, what you'd end up with is the same quad mesh, but refined to a 3x3 grid. And what that lets you do is, if you have a topological mesh that's very curved, you can make it very close to being planar. And the second step is you take all of your hexahedra and you subdivide them into 7 like so, at the bottom. And now if you look at the mesh that you end up with at the end, you can choose the vertices that you insert throughout the process so that almost all the faces are planar, except the two faces that, except the face that, so if you have those patterns of 7 hex, one on the left, one on the right, they share one face. If you take the hexahedra that contain this face, there are 2 of them, and they form a warped bicuboid. If all we have to do in order to complete the construction and get a geometric hex mesh is find a geometric hex mesh of the warped bicuboid. So that's the most interesting one, the configuration that we know from a theoretical perspective. We also have this pyramid, which topologically it's hard to find by hand, but we've known that there are solutions for a very long time, then we have them. And they look very close to being planar, but they're not exactly planar. And so what I'll be discussing today is how can we take those meshes that are, for the one on the left, almost planar. The one on the right uses very curved face, so I don't think that one can be extended to a geometric mesh, but the one on the left does look like you can make it into a geometric mesh. And the first hint that suggests to me that it is possible to make a geometric hex mesh from this is that if you try to numerically take this mesh and optimize the planarity of the faces, so you try to minimize the angle between the 2 triangles of each face by just moving the vertices by a small amount, you can make that objective function basically as small as you want, which is not the case with the other mesh that I showed earlier. So that tells me that it's probably possible to make a geometric mesh of the spindle, which is this shape here. But numerically there are no way for you to just get a geometric mesh directly. So to simplify a problem, the first trick that we're going to use is we're going to greatly reduce the number of degrees of freedom that we need of the problem by just considering the symmetries of the mesh. So the spindle has 16 symmetries, but our hex mesh only has 4. So by using those 2 symmetry planes, we just enforce that each quadrant is the same. So we've essentially divided the number of unknowns by 4 already. And what we also know that our mesh is already close to a geometric realization. So we know that most of the vertices in our final mesh are going to be very close to the ones that we have already. So the first thing we are going to do is we take some vertex V on our approximate mesh, and we decide to fix its position. Secondly, if you have 3 vertices in a single plane, 3 vertices of a face that you know, you can project the 4th 3 vertices of face. You can project the last vertex of the face in order to the closest point. Again, since we know that our geometric mesh, our approximation is very close to a geometric mesh, we expect that the projection onto that plane is going to allow us to make a geometric mesh. And then finally, if you have if you know three vertices of three different faces of a hexahedron, you can use those to define three faces and find the forced intersection, find the forced location of one of the corner of the hexahedron. So you have a bunch of operations that we have a bunch of operations that let us take our approximation and force the location of certain of the vertices of the mesh. Now the problem with that is depending on the order in which you choose the different operations, you might end up with a configuration where the mesh is very close to planar, but some of the faces are still curved. And the only way to fix that would be to solve a system of polynomial equations exactly, which ends up being very difficult. But what's nice is because we have a lot of different order in which we could choose to round vertices or project them, there's basically a tree of different possibilities that we can have to convert our approximation into a geometric mesh. If we try a lot of them, we can end up with another bad configuration that is much nicer to deal with. So this mesh has inverted elements, but all the faces are strictly planar, even though the mesh intersects itself. And what's nice about that is that all the difficult constraints, all the equalities are solved already. And all we have to do is to convert this mesh into a geometric mesh is we take, when we project a vertex, so when we round it, we can slightly move the vertices around in order to get a geometric mesh where the faces don't intersect themselves anymore, because the constraints of non-intersection come down to inequalities instead of equalities, so they are much easier to solve just by moving the vertices around a little bit. You don't have to find an exact symbolic solution. And what we end up with is a mesh that looks virtually identical, although some edges are a lot shorter here, to the trilinear mesh, but it is completely geometrical. And so that's a proof of concept of a technique to take those meshes that are nearly geometric and convert them into a geometric mesh. In the future, the most interesting configuration is still the bicuboid, and we hope that we can use those same techniques basically to either find a topological mesh that can be extended to a geometric mesh of a world bicuboid, or help convince ourselves that there is no such geometric mesh and try to narrow down the conditions under which a topological mesh can be extended into a geometrical mesh. Thank you. That is all I have today. Yeah, any questions?
If anybody has questions?
I have maybe one very general one. So very nice talk. I enjoyed it a lot. I was just wondering, do you have some applications in mind where it is very important to have a geometric mesh? So like
no, it's more a theoretical concern where I think that it's not a coincidence that we have so many theoretical results for tetrahedral meshes. And for hexahedral meshes, in terms of geometry, we know nothing. And then if you look at practical applications, we have tons of practical tools to generate tetrahedral meshes, but almost none for hex meshes. And I think the two problems are linked, and this can help kind of figure out the problem.
Mm-hmm. Yeah, it seems to be really a very interesting one. So I never really looked into that, but did people study this more from, let's say, a Voronoi diagram point of view? Because, like, if you could find some type of Voronoi diagram, then you would also always end up with a geometric mesh if you can guarantee to get only hexahedra.
I don't think so. So what people have done is they've proven, for example, that you can that there are transformations that can be done geometrically, or that preserve whether or not a mesh is geometric. So if you can prove that your mesh can be reachable using those transformations, you know that it's not possible for it to be geometric. And people have also come up with a bunch of different constructions. Like there's a paper by Alexander Schwartz and Gunther Ziegler where they show a bunch of different different constructions that you can do geometrically. And for example, they showed that you can use that to make a mesh where you have the boundary is 6 faces, so it's just a hexahedron, but you have an even number of hex inside of it instead of an odd number geometrically.
Robert, you want to say something?
Yes, do you understand?
Yes.
Yeah, we can hear you.
Yeah, I have a question. Geometrically, does that mean that the late product, the vector product at the edges, is positive?
Yes, it must be strictly convex as well.
Yeah, and for numerical calculations, usually to judge the quality of a mesh, a good measure is a normalized Jacobian. Just normalize the edge length and compute the vector product. So if this is sufficiently positive, then it is judged a good mesh. So is it possible to give some, let's say, epsilon and for example, the pyramid mesh, and to guarantee that the vector product, the normalized vector product, is not smaller than that epsilon?
I don't think what I've done can provide any such guarantee. Like it's guaranteed to be greater than 0, but nothing more than that. So the example that I showed, you had one of the quad almost looked like a triangle because one of the edge was so short. So
okay, yeah, thank you.
You're welcome.